So moving forward into the controllable and reachable subspaces sections, so far we have discussed about the LTI systems and in fact the continuous time, linear time varying and linear time invariant systems. So one of the important conclusion we reached that for the continuous time systems, the controllable subspaces and reachable subspaces basically coincide. Now the natural question arises whether they also coincide for the discrete time scenario. So today we'll start with the discrete time systems. So consider the discrete time LTV system given by these AT and BT pairs. Now T is belongs to a set of integers. So a given input u transfers the state x naught at time t naught to the state x1 at time t1 given by the variation of constant formula. So we would be using the similar concepts that with which we started while doing the analysis for the linear systems. So again we want to express how powerful the input is in terms of transferring the state between the two given states. So these were the two subspaces we have discussed for the uh, continuous time systems. So again recalling them for the discrete time systems, given two times t1 greater than t0 greater than equal to 0. So note that again that do not forget in fact that t here belongs to the set of integers. So we are talking about the discrete time systems. So the reachable or controllable from the origin on within this interval t0 to t1 consist all those states x1 for which there exists an input starting from, so it would be a sequence of inputs starting from u t0 to up to t1 minus 1 that transfers the state from x t0 equals 0 to x1, which is given by this set. So this is the reachable subspace. In a similar way, we define the controllable subspace where we want to see or we want to form a set of all states x0 for which we could ensure that there exists an input u that transfers the state from x0 to the origin. So again there are two concepts. One, from the origin we want to take the state to some values, let's say x1, which would give me the reachable space. The controllable space, I am looking for all those points where starting from where I can reach to the origin. Okay. So talking about the Gramians in a similar way what we had discussed for the continuous time system. So we define two Gramians. One is the reachable Gramian and or reachability Gramian. Another one is the controllability Gramian. So the idea of introducing these Gramians is to characterize the complete subspace. So for the reachability Gramian, it is given by this summation starting from t0 to t1 minus 1, the state transition matrix from t1 comma tau plus 1 into b tau and their transpose. Now note here about the controllability Gramian. So here the summation is taken from t0 to t1 minus 1 and phi is t0 comma tau plus 1 and b tau and their transpose. So here you need to make a bit of attention that the discrete time controllability Gramian requires a backward in time state transition matrix, because say for example if starting with tau is equal to t0, it would give me phi t0 comma t0 plus 1 and the two arguments within the state transition matrix says that starting whenever the input is applied at this time, I am collecting the response at this point. So I need to compute the backward in time, which is quite visible in the state definition of the state transition matrix. So it imposes some restrictions in the sense that this matrix is well defined, this state transition matrix is well defined only when all these matrices, the matrices at different times are non-singular. Right? Say for example, if we see the response of the discrete time system, this is how we computed the response by using the uh, advances in the time, because in fact solving or computing the solution of a discrete time state space system is basically solving an algebraic equation. So we use some recursions to compute this solution. Now if I want so this controllability or controllable subspace is basically we want to characterize all these points starting from where I can reach to the origin. Now if I want to compute this point x of t naught, what I need to do, I need to pre-multiply both sides by the inverse of these matrices. So I need to compute this one. So to compute this one and for the solution, that all these matrices should be non-singular. Okay. So when this does not happen, the controllability Gramian cannot be defined. Then the characterization of the subspaces in terms of the subspaces given by the Gramians. So given 2 times t1 greater than t naught greater than equal to 0, the reachable subspace is basically equivalent to the subspace formed by the image of the reachability Gramian. Moreover, if x1 belongs to this subspace, is equivalent to saying that I can write x1 is equal to reachability Gramian into some vector eta1. This control, which is given by here, can be used to transfer the state from the origin to some point x1. Okay. In a similar way, we gave the result that the controllable subspace is equal to the image of the controllability Gramian. Moreover, if x0 belongs to this image of or belongs to this space, this specific control for some eta naught can be used to transfer the state from x0 to the origin. So we won't be taking going through the proof for this, because we have already seen the proof for the continuous time system, but which you can do by yourself. So the idea here, we need to do the proof in 2 parts. Basically both ways implication this. That is to say, if x1 belongs to this subspace, implies that x1 also belongs to this reachable subspace, the other side implication. So once both these implications are shown for the reachability Gramian and controllability Gramian, then you could have the proof for this theorem. Now for the LTI system, when we discuss about for the continuous time scenario, we introduced one matrix which we call the controllability matrix. So again, the controllability matrix can be computed in a similar way. So there are 3 important parts. One is the discrete time system itself, the controllability and the reachability Gramian. In addition, we define the controllability matrix, and we set up one relationship between the Gramians and the controllability matrix, right? So this was one of the key results where we have shown the equivalence between all the subspaces formed by the reachable subspace, its characterization with the help of the Gramians, and for the LTI case we use the controllability matrix, and we have shown the equivalence of all the subspaces. So in the discrete time case, the notions of controllable and reachable subspaces coincide only when the matrix A is non-singular. One of the reasons we had seen that because you won't be able to compute the solution, or you won't be able to compute the x0. Right? Now, if it does not happen, it might be possible that at some time this matrix A could be non-singular, or could be singular. In this case, the reachable subspace would be equal to this space given by the image of the controllability matrix, and this both these spaces would be a subset of the controllable subspace. Okay, so try to visualize what is happening here. Now if the matrix A is non-singular, it is pretty much clear that we will have both sides equivalence. Okay, but now let's say we have this bigger space and a subset, or sorry, the subspace of this we here we have all the points, the which is the reachable subspace, where from origin we want to go to x1, right? Now this subspace says starting from x0 we want to go to origin, right? So this inner space is basically the reachable subspace, and the outer one is the controllable subspace. So what does it tell? Let's say if I pick any point, here, then it says that there are some points or there are some states from starting from where I can go to the origin, but these points starting from origin I cannot go to these points because these points are out of this subspace. Okay, so this is is the geometrical meaning. The reverse inclusion does not hold, because if the reverse inclusion holds, then it means to say we would be having the equal sign with which we were having in the main result. So that there are states x1 that can be transferred to the origin, but it is not possible to find an input to transfer the origin to the states, to these states. Okay. So because of this, one must study reachability and controllability of discrete time systems separately. Now for the continuous time system, we could study either of them and prove our results. Now for the discrete time, if the matrix A is non-singular, or if the matrix is A is singular, then we need to study separately both these concepts, the reachability and the controllability. Again, the proof could be done in two parts, similar to what we had done previously. This equivalence comes from the controllable subspace and its characterization, and this reachable subspace, you need to only show these two equivalents, both sides. Okay, which you can do either starting from reachable subspace result or from controllable subspace result. Okay. Note that here that whatever the results we are talking about, where we have considered the controllability Gramian, it implicitly assumes that the matrix A is non-singular. Okay, because why? Because the controllability Gramian includes the backward computation of the state transition matrix, and the backward computation is only possible if the matrix A is non-singular for all time t in case of time varying, and in case of time invariant it should be only non-singular. Okay.